It seems this is the week of the Transformers successor. SakanaAI just dropped a brand new paper called Transformers Squared. And in this paper, they detail a method in which a large language model can be updated at inference time based on the prompt given. And the best part, it's open source. They've already released the code to do this, and it can be applied to any open source model. Let me break it all down for you right now. So this is the paper, Transformers Squared Self-Adaptive LLMs by SakanaAI. And if you don't remember, SakanaAI is a cutting-edge AI research company out of Japan. They were the ones that produced the paper and code for the AI Scientist, which I made an entire video about, and it basically automates the ability for AI to perform open-ended scientific research. So very, very cool stuff. So I'm going to dive into the details of the paper, but the gist of how Transformers Squared works is it basically takes two passes at a prompt. During the first pass, as we're seeing here with this nice little graphic, we're actually taking the user query, running it through the model, and trying to understand what the query's task is. So is it a math question, as exampled here? Is it a coding question? Is it a logic question? And then it actually updates its model weights at inference time to better answer the query at hand. So we've seen a lot of this. In the paper that I just talked about out of Google, the Titans paper, they did a lot of the same thing, and it seems like that is the new trend, trying to make models less static. And that is one of the big problems that we've had with the Transformers architecture to date. Basically, once the training is done, that model is fixed in time. It does not learn new information unless you give it external information via RAG, for example. But what if it could? What if you could take a model that had a lot of core intelligence and then allowed it to learn and update its models over time without a huge post-training cost? This potentially could be another scaling law. And so that is what Transformers Squared does. So let me break the paper down. Self-adaptive large language models, so that is what Transformers Squared aims to be, aim to solve the challenges posed by traditional fine-tuning methods, which are often computationally intensive and static in their ability to handle diverse tasks. So rather than fine-tuning, they are proposing a new method in which you almost surgically go into the model and change very specific weights at test time, at inference time, based on whatever the user's prompt is. So here is how they describe it. Self-adaptation framework that adapts LLMs for unseen tasks in real time by selectively adjusting only the singular components of their weight matrices. That's a fancy way of saying it's updating its weights, but only the ones that are specific to the prompt at hand. And that is why the two-pass approach is necessary. The first pass being, let me understand what the prompt actually is asking for. So let me explain what the two passes are. So the first pass is a dispatch system that identifies the task properties. And then the second pass is using task-specific expert vectors trained using reinforcement learning are dynamically mixed to obtain targeted behavior for the incoming prompt. Again, simply put, understanding the prompt and updating the weights to better answer the prompt. Our method outperforms ubiquitous approaches such as LoRa with fewer parameters and greater efficiency. And I will show you the performance in a little bit. Now, again, this isn't the first time we've seen test time training. And in fact, there was literally a paper called Test Time Training that I covered. So this is kind of the cutting edge technique that a lot of companies are using to update the model, not during pre-training and not during post-training, but during inference time, which is a really interesting approach to make models less static, more dynamic. And the cool thing is it also works with vision models, and in fact, really well with vision models. All right, so let's talk about how model training works today. This is before Transformers Squared or any of the other papers that we've talked about recently. LLM post-training has sought to optimize a model for a wide range of capabilities in a single extensive training session, fine-tuning. One-shot fine-tuning framework is ideal from a simplicity perspective. It is also difficult to achieve in practice. For instance, post-training is still highly resource intensive. There tends to be notable performance trade-offs when introducing additional breadth to the data, making it challenging to overcome overfitting and task interference at the same time. So if you're not familiar, a model, when being created, after it's done with its pre-training, that initial run where you're instilling all of this knowledge into the model, then you could do something called post-training, in which you're guiding the model on how to respond, you're giving it additional information, you're basically showing it how to follow instructions instructions properly. So you're taking that raw knowledge and you're giving it some guidance on how to use the knowledge. But that's very costly and very inefficient to do. And what they're proposing here is as follows. The self-adaptive model offers a more flexible and efficient approach. Rather than attempting to train an LLM for all tasks in one step, here's the key, expert modules can be developed offline and augmented to the base LLM on demand. This allows the model to dynamically modify its behavior based on the task at hand without the need for constant retuning. It supports continual learning, enabling the model to add new skills over time without catastrophic forgetting. So remember back to the Titans paper that we just covered. Traditionally, when you add a lot of new knowledge to a model, the model tends to forget other things. And that's the memory problem that Titans was trying to solve for. So another approach is also trying to solve for that issue. Self-adaptive LLMs mirror a well-established principle in neuroscience and computational biology, which, let's pause for a second. It seems like all of the companies that are coming out with the next iteration of transformers seem to be trying to model its architecture much more closely to how the human brain works. And that is the basis for a neural network. That is why it was created originally, because that's how the human brain works. The brain activates specific regions depending on the task at hand and dynamically reconfigures its functional networks in response to changing task demands. So if you're doing some creative writing, if you're doing math, if you're writing code, these are different use cases and your brain behaves differently based on whatever task you're trying to accomplish. And now they are mimicking that with transformers squared. So again, think about you have the core model and then you have these expert modules. So an expert at coding, an expert at math, an expert at creative writing. And at inference time, at test time, the framework tries to understand what the task at hand is, and then like a surgeon goes in and changes the model weights using those expert modules. And it's very, very efficient according to this paper. So these expert modules are fine-tuned via techniques such as low-rank adaptation, which we've covered on this channel. These expert modules can then be dynamically composed at runtime based on the task demands, a process that can be efficiently managed through mixture of experts like systems. But it's not that easy. And so we're going to cover some of the challenges that need to be solved, which they apparently did, with using this method. So first, fine-tuning LLMs to create multiple expert modules significantly increases the number of parameters that need to be trained. Obviously, you have a bunch of other submodels, and all of those additional submodels just take more and more parameters. And second, these expert modules are often prone to overfitting, something that is a problem in the world of AI in general. A phenomenon especially prevalent when training on smaller datasets or narrow task domains. So if you're looking to create really narrow expert modules, you are going to run into the overfitting problem. And then third, the flexible composition of these expert modules also presents largely unresolved challenges currently posing as open research problems. Basically, it's never been done before. So their proposal to solve it, singular value fine-tuning. A novel parameter-efficient fine-tuning method, so PEFT, which you've probably heard of if you watch this channel at all, to obtain effective building blocks for self-adaptation. SVF works by extracting and tuning only the singular values within the model's weight matrices. That's the important part. It is, again, kind of like a surgeon. It goes in and really, in a very narrow manner, changes only what is necessary to give that model that additional expertise. So here's a nice graphic from the SakanaAI blog about this paper. On the left, we have the LLM brain, and we can see that it's all basically one thing. But on the right, what they've actually done is segmented the different parts of the brain or the LLM into language, reasoning, and coding, which allows it to, at inference time, know which parts of the brain or the LLM need to be updated. So if we're looking at figure 1, which is what they referenced in that previous paragraph, we can actually see what's going on. So we have the user query, and the self-adaptation vectors are kind of like that brain diagram that I just showed you. So we're going to go in and we're going to figure out, based on the query, we're going to run it once and see, well, is it math? Is it coding? Is it somewhere in between? Who knows? It could be anything. And then from that, we're going to update the weights. So this is a math question. Then we come in for the second pass in red, and we can see the red arrow right here. We go in again after the weights have been updated, and then we actually have the answer. And how does it perform? We show that SVF consistently outperforms traditional strategies for efficient fine-tuning, such as LoRa. and at the same time with orders of magnitude fewer parameters. So what we're going to see in the actual results is it performs better, not exponentially better, but it is orders of magnitude more efficient. So how do they actually figure out which weights to update? They use two methods. So first they use SVD, singular value decomposition, which offers a fundamental view of matrix multiplications. Then cross entropy method, CEM, which is a Monte Carlo method for importance sampling and optimization. Both of these is basically just saying, how do we figure out what to change? So a little bit more detail about singular value fine tuning. So it is a key building block of transformer squared. It offers an extremely efficient parameterization for fine tuning and provides inherent compositionality for adaptation. Basically, it works well. So conventional fine tuning techniques often aim to augment pre-trained models with new capabilities by modifying their weight matrices. However, in large-scale transformers, these weights are already rich repositories of abstract knowledge, thanks to the breadth of the pre-training data and expansive architectural design. And so their solution is, instead of seeking to add new features, take what you already have and make them better. And so there are three ways that they've done this. Now, I actually had to get a little help from AI to help me understand what these meant and to give some analogies. So I'm actually going to reference what I got from AI, and hopefully that helps you understand what these three things are. So first, negligible parameters. So it says, like choosing the best knobs to turn. Imagine tuning a massive stereo system with hundreds of dials and buttons. Most methods for fine tuning a system like a LoRa involve adding a bunch of extra knobs and switches to control things. It works, but it's bulky and complicated. On the other hand, it figures out which existing knobs are the most important and only tweaks those. So that is negligible parameters. Next, high compositionality, building with Lego blocks. So a different analogy. Think of the weight adjustments in a model as Lego blocks. In SVF, each parameter is like a separate Lego piece that can be easily snapped together in new ways. You can combine or modify them to build something new. Other methods like LoRa are like glued together Lego structures. Once the pieces are stuck together, it's hard to take them apart. And so reusability is a big part of SVF. And then principled regularization, coloring inside the lines. So for this, if you give kids crayon and tell them to color and there's no guidelines or anything, they're just gonna color a white piece of paper or whatever it is, and there's really not going to be a lot of structure to it. But with principled regularization, it basically gives them a coloring book and some guidelines, and maybe they're coloring a penguin, for example. So it gives that black and white outline of what to color, and then it does a much better job of coloring it because there's actually some kind of semblance of guidelines. So let's again dive into the two passes. The first pass, you're going through trying to figure out what this task is actually about. And so how they do that is with pretty straightforward methods, actually. So there are three methods. One, prompt engineering. So our most basic approach involves constructing a new adaptation prompt, which we use to directly ask the LLM to categorize the input prompt. So here's an example of it. So analyze the given question and classify it into one of four categories: code, math, reasoning, or others. Follow these guidelines. So the input is basically categorized into one of those, then some additional instructions, and then how to actually format the output. So very traditional prompt engineering. Next is a classification expert. So it's a direct extension of the prompt engineering approach and comes from using a specialized system to handle task identification. I believe what they mean is a separate system model that will actually do the classification into one of those four categories. And then third, few-shot adaptation. So leveraging additional task information by assuming extended access to its test time conditions beyond individual prompts. So just using the same systems as before, but being able to iterate multiple times. All right, so how does it actually perform? Well, let's start looking. Now, what we're looking at here in these four charts are the performance of Llama 3 8B Instruct using their new method. Now, the dotted line, the dotted black and white line right there is the score based on the original Instruct model of Llama 3 8B. Then in red, we see what happens at test time, and then in blue, we see what happens at training time using this new method, Transformer Squared. So you can see across the board, it is performing better. And specifically, the training time is significantly better. We find that SVF provides considerable and consistent performance gains across nearly all tasks and base models. This observed trend extends also to the vision language domain, which is very interesting. SVF requires considerably fewer resources with less than 10% of the training parameters of our LoRa implementation. So better, but much more efficient, as I've said. And it applies to different models. So all of our transformer squared adaptation strategies show improvement across Llama 3 8B instruct and at least 2 out of the 3 tasks for Mistral 7B instruct and Llama 3 70B instruct. So this isn't model specific. And so we're seeing a lot of those results right here. These are the 3 different base models right here. Then we have the LoRa implementation, and we have the SVF implementation, which is the basis for this paper. And as we can see in bold, for GSM-8K, performs better across the board. For MBPP Pro, it performs better in 2 out of the 3, and same for Arc Easy, 2 out of the 3. So really good. But remember, the key is it performs better, but much more efficient. But you're probably asking yourself, okay, if it has to take 2 passes, isn't that going to be really expensive or take a lot of tokens? And the answer is a little bit more, but not really. So let's take a look here. So in this table, we're seeing the time cost of the second pass inference. Here we have math, human eval, and arc challenge, and these are in seconds. So here are the first scores, which are really a small fraction of the second pass, and then we have the second pass. And you can kind of think of the second pass as a normal pass. So it really doesn't add a ton of time to the overall run of these benchmarks. Now, the exception to that might be the arc challenge, but they actually explain that down here. So the second pass inference time is the time spent on solving the problems, and the first pass inference time is the time for self-adaptation. So just an explainer of what you're looking at. Then, while the additional inference pass might appear to double the overall runtime, it is important to note that inference time primarily depends on the number of tokens generated. And the ARC challenge in particular, the ARC challenge's cost ratio is large because they are single choice problems, and therefore the cost of the second pass is also the same as the first pass. So that's why they're very similar in time. And how good is it at figuring out what type of task is it? Well, that's what they call the confusion matrices. And that's kind of a cool name. So what we're seeing here is Llama 3 8B based on prompt engineering. Here's the same one based on a classification expert. Here's prompt engineering classification expert, and then Llama 3 70B prompt engineering. And what we see is if it's 1.0, that means it has perfectly identified the task. And what we see is for Llama 3 8B prompt engineering, the ARC challenge was actually the one it kind of struggled with, but it still did quite well, 77%. Then using the classification expert, really, really good, 95, 98, and 97. And we're seeing the same results basically across the board. The only one it really struggled with was prompt engineering specific to Llama 3 8B, specific to the ARC challenge. All right, so in conclusion, this is a new method that allows the kind of traditional transformers architecture to learn over time, and it happens at test time, and it's really efficient. So another great example of a cutting edge research lab creating what may be the next generation of the transformer model, transformer squared. The idea of allowing these model weights, which after the original training are really fixed in time and don't change to change, is a really cool idea and allows the model to evolve over time rather than continuously having to come out with new models over and over again. And so we'll see if this new method catches on. I'm very excited about it. Definitely try it out. They posted the code. I'll post it down below in the description so you can try it out yourself right now. If you enjoyed this video, please consider giving a like and subscribe, and I'll see you in the next one.